This is a video to go with this particular worksheet. In this case, I'm going to be out of town at a conference, but in case you're homesick, this video will help you get through the worksheet. So this unit is all about reaction rates. What makes reactions go fast, slow, etc. The entire time we are doing this, we are focused on the reactants because, well, what's reacting? Reactants. Therefore, the reactants dictate how fast the reaction goes. So the first thing you need to know is that the basic way to find the rate of change in some chemical is the change in concentration over the change in time. And we use brackets to represent concentration, which remember is moles per liter or molarity. Okay? So let's take a look at the first problem here. It says in a reaction between butyl chloride and water, the concentration is that at the beginning. After 4 seconds, the concentration is that. Calculate the average reaction rate over the given period of time. You just follow this equation. But remember, to do concentration, it's final minus initial. And that means you're going to put that value in first. You're going to subtract that value. You are going to get a negative rate value, a negative molarity per second. And what does that mean? It means it's disappearing. It's being used up. So the reactants will always have a negative reaction rate, while the products will have a positive reaction rate. So right now, we're just focusing on individual chemicals in a reaction. So here's another one. Take a look at this equation. H2 plus Cl2 makes 2HCl. Calculate the average rate of H2 consumption. Well, here's your final, here's your initial, subtract them, divide by your time. Same thing for this one. Here's your final, here's your initial, subtract, divide by 4. Okay, and each time you're going to get molarity per second as your label. Now notice, they didn't give you that, right? But you guys, rate is just like moles, mole ratios. So I'm totally making this up. This is not the answer. But let's say we found out that the rate for H2 was 5 molarity per second. All right. So 5 for the H2. And you can simply do a mole ratio, but with the rates. That's why I'm not writing a label. Well, we have 1 to 2. So this is going to change at 10 molarity per second. I mean, think about it. Every time you use, let me erase a little bit of this here. Every time you use one of these, you make 2 of those. So if this disappears at a rate of 5, isn't this going to appear at a rate of 10? And that's all you have to do on that one. Again, that's not the answer. Make sure you do your answers and use them. So then 5 says, okay, what would be the concentration after 4 seconds? Well, this is kind of like speed, right? You're driving 60 miles per hour. How far do you get if you drive for 4 hours? Well, doesn't the hours cross off and you get 240? It's the same thing. So let's just say that our answer to 4 is 10. That means every second the concentration changes 10. Well, after 2 seconds, it would be 20. After 3 seconds, it would be 30. After 4 seconds, it would be 40. Okay? And that's all you have to do on those. By the way, I like to do cursive S because if I write it like that, it starts to look like a 5. I know, crazy. Now come down to this next one. It says, in a reaction, Mg plus 2HCl makes H2 and MgCl2. We have 6 grams of Mg at 0. After 3, we have 4.5 grams. Calculate the average rate. Now, normally we do change in concentration. Guys, this is a solid. We're not going to be able to get concentration. That's for a solution. So don't worry about the fact that you don't have molarity. Just do change in mass divided by change in time, and you'll get grams over minutes because they gave you minutes. So it's totally fine. Do the same thing as above. All right. How do you do this part? So we're going to focus on this equation. 2N2O5 makes 4NO2 and O2. All right. So here's some data. Number 7 says, calculate the average rate of consumption for N2O5 for each time interval. So the first time I want you to look at 0 to 20. Again, final minus initial divided by the time. In this case, it's going to be minutes, right? So do that one. Then I want you to do from 40 to 60, and then I want you to do from 80 to 100. So there are 3 answers here. They're all going to be molarity per minute. They're all going to be negative because this is a reactant. You're using it up. Now, look at the balanced equation. How would the average rate of the production of NO2 compare to these values? Well, look at your mole ratio, you guys. 2N2O5 is to 4NO2. So let's say this has a rate of change of 10. Isn't this going to be double? Because aren't these in a 1 to 2 ratio, right? So that's why. Mole ratio, same thing as we mentioned above. Number 9 says, compare your answers in number 7. What happens to the average rate as the reaction goes on? So you're going to have 3 values in this problem. What you should see is that the values decrease. What does that mean? It means in the beginning, you have the greatest rate. And why is that? This is a key concept to reaction rates. Well, in the very beginning, all you have are reactants. All reactants. They're banging into each other and colliding and reacting. But as they get used up, there's less molecules bouncing into each other. You have less reactions, so the rate decreases. So that's what we're getting into on this one. You should see that it decreases. And then number 10 is use collision theory to explain the phenomenon. Collision theory simply says that things must collide in the right orientation with enough energy. So just because 2 molecules collide doesn't mean they're going to react. They have to collide in just the right way with just enough energy for there to be a reaction. And that is how you do this worksheet. Now go do it.